Okay, so here's the plan for today. We're going to do this word problem. We are going to, after we do the word problem, we are going to talk about more word problems, and then we're going to talk about the review. So the review, I think I posted it yesterday or the day before, I don't remember. And I sent an email to everyone, and I put it in Canvas. So I'll bring that up, and we'll look at it, and we'll talk about it, okay? Your test is Thursday. Okay, so a person, 98.6 degrees, is their normal body temperature, died in a room. The room is being held at a constant temperature of 72 degrees. If the temperature of the body is 92 degrees when the body is found, and 89 degrees 2 hours later, then what is K? K is the constant that we're looking for here in, what did we call this thing? This is Newton's law of cooling, right? Where the capital T is the temperature of the room, U naught, or U sub 0, is the temperature of the initial temperature of the object. In this case, it was a body. We assumed it to be 98.6. K is the constant, we don't know. Little t is how much time has elapsed, right? And I showed you last time that if we plug in t is 0, we get the person's temperature, 98.6. So what we did is we plugged everything in, and we got this function that is an exponential function. The only thing we don't know is what k is. So if we can find the k, what we'll be able to do is determine the temperature of that person's body at any point in time, right? Any point in time. So we have to set out about finding the k. That's the difficulty, all right? Do y'all remember this enough for me to continue? Yeah? Okay. So reminding you now, U of 0 gave you 98.6, right? And that was the temperature of the body at death, right? When they died. We walk into the room, we don't know how much time has gone by, do we? Right? We don't know how much time has gone by since we found, since the person died. That's what we're trying to figure out, right? When did the person die? So, but I know the temperature was what when we walked in? 92 degrees, right? Was it 92? So here's what I know from that. U of not U of 92. U of some point in time, which I'm going to call T1, is 92 degrees. Do you all agree? At some point in time when I walk in, T1, I take the temperature, it's 92. Then 2 hours later, it's what? 89. So how do I say 2 hours later? I say U of the time I walked in, T1 plus 2 must be 89. So this is the temperature when we find the body, right? And this is the temperature 2 hours later. Does everyone understand what's going on? T1 is what we're trying to find in the problem right now. We want to know, right, how long the person had been dead. So when I walked in the room, that's T1. That's how much time has passed since the person's died. That's what I want ultimately. Do you all understand that? Okay, now we need to use this function kind of against itself so that we can figure out what k is. I know that when I plug in 0, it spits out 98.6. When I plug in T1 up here for T, it should spit out 92. And when I plug in T1 plus 2, this whole thing should spit out 89. Yes? Okay, so I'm going to write that down on the next page because I'm out of room here. And I'll be using this, so I'm going to take it with me. Okay, the fact that U of T1 was 92 means that 72 plus 26.6 e to the k T1 must be 92 degrees. So all I did here was I took the function, I replaced t with T1, and I know that when I do that, it's going to spit out 92. Yes? I'm just writing that down. That's information. The other information I have is that when I plug in T1 plus 2, it needs to spit out 89. So I'm doing the same thing, replacing here. Replacing T with T1 plus 2. All right. Now, I know it may seem like, what are we doing? Like, where are we going with this? What I've done is I've created two equations, haven't I? And I have two things I don't know. I don't know what K is, and I don't know what T1 is. And I want to know both of them, don't I? Generally, when you have two equations and you have two unknown variables, you can solve for them. Now, sometimes it's very difficult to do so. Sometimes it's easy. Let's see what happens here. So what can I do to try and figure this out? This is tricky. This? Our base here is E. Right? The base here is E. This is a number in front of it. So let me do something real quick. I want to separate these two. Remember, these are two different equations, right? Let me work with this second one for a second. Just tell me if you agree with this. What did I do there? Just distribute the K through the parentheses. And now I'm going to do something. I want you to see if you follow. Still working with the second equation. I took this piece right here and I rewrote it as these two. Bless you. Now, what I'm doing here is I'm using a property of exponents that you may or may not recall, so I'll put it over here on this board. We have property that says if you have x to the n times x to the m, it's x to the n plus m, right? If you have the same bases and different powers and they're being multiplied, you can put it into a single base and you add the exponents. But it also goes backwards. If you have a single base with two things added, you can split it apart into a product of two things. That's what I'm doing. I'm going right to left here, and I'm using it right on this piece right here. This is like my x to the n plus m is equal to x to the n times x to the m. Do you all see it? Yes? Now, the reason why I did that is because I noticed that up here, see up here? I have e to the kt1 right there. And by doing this, I actually have e to the kt1 right here also. So what I've done is I've made the same thing appear in both. Do you see it? Any questions? Okay, so let's see where I can go with this now. I would like to take this first equation up here, and I'd like for us to solve it for e to the kt1. Like, try and get this by itself. So what would you do? Subtract 72 on both sides first, right? Subtract 72. When I do that, I get 26.6 e to the kt1 equals what? 20? Okay, let's get the exponent thing by itself, so let's get rid of the 26.6. So divide both sides by 26.6. Break out your calculators. We're going to need them. Thought I brought mine. I'm pretty sure mine's in here. Yes, it is. 20 divided by 26.6. Okay, so e to the kt1 equals 0.7, let's say 52. Is that all right? Approximately? Yes. Where? Right here? Divide both sides by 26.6. Oh, right here, this equation right here. Just take 72, subtract 72 on both sides. It goes away here. 92 minus 72 is 20. Is that okay? So remember, the whole point of this was that I noticed I had e to the kt1 here. This right here looked nasty. I kind of broke it up. I said, I can split it off. See, this is the e to the kt1 also. But what is e to the kt1 according to what we just did? 0.752, right? So now I can go back to this equation, and I can replace e to the kt1 with 0.752. You see that? And that's going to be a very nice thing, because if this is a number, look, this blue thing is a number. Everything else here in this equation is a number. Even the e, right, is a number, except the k. So I have an equation with just k in it, which is what I need to solve for k, isn't it? Just an equation with k in it. So I'm kind of eliminating the t1 here by doing this. So continuing, I'm going to put a dotted line here just to let you know I'm continuing this, but after I did this, right? Okay, so now this is 72 plus 26.6 times 0.752. I put it in parentheses. And then I still have e to the 2k equals 89. Agreed? Now, this is an equation, right? It's an equation. It is an exponential equation because the variable we're trying to solve for is stuck in the exponent. How do you get variables out of exponents? Pull it out. But before you pull it out, you have to bring in what? Logs. So I need to do that, but I can't do it yet. Remember, before you can bring a log in, you've got to have this thing by itself. So let's do order of operations. Let's multiply these two numbers together. So on your calculator, take your 26.6 times 0.752. And you get about what? 20.03. Yeah. So we'll go 72 plus 20 point, I don't know how far we want to go. I'll just say 0, 0. I'm getting 3. Is that what you got or no? Okay. E to the 2k equals 89. What next? Subtract 72. When I subtract 72, you get what? 17. Divide by 20 now, or 20.03. You should get a number smaller than 1. Are you 0.849 something? 49. Let's go 499 or something like that. Everybody still with me? Questions? Okay, how do you solve this now? We've isolated this exponent. Natural log on both sides, right? That way we can pop the 2k out in front. So, I'm sorry? They will. The natural log and the e? Yes, but don't forget you have to do it on both sides, right? Okay, so that will drop out now, and we'll get 2k times natural log e equals natural log 0.8499. All right? But natural log of e is what? 1, right? So we're getting, really here, 2k is natural log of 0.8499. Let's go ahead and take natural log of 0.8499. Right, we do this on the calculator. I get negative 1.626 or something like that. Yep. So we have 2k equals negative 0.1626. Finally, divide by 2. And k is equal to negative 0.081. I'll go 3. Okay. Have we answered the question of when this person died? No. All we've done is found the constant that gives us our exponential decay of temperature. It's showing the rate at which the temperature is dropping for this body. So I'm going to go back up to this. This is my original thing right here, right? I'm going to grab this and go to another page. I'm going to rewrite this, but I'm going to replace K with what we just got. So I'm going to say, so here's where we are. That was negative 0.0813 T, right? That's it. This is the function that describes the temperature of the body in this particular room at any point in time. Right? That's what it is. As they're dead, yeah. Who cares, right? They're already dead. So that's it. Now let's try and still answer the question here. We want to know what the time was, right, when we found them. So what was their temperature? What was the temperature of their body when we found them? 92. Do you agree? So remember, this left side is the temperature of the body. If I replace this with 92 right now, the only thing left in the entire problem that needs to be resolved would be the T, which is what I want, right? So just if you replace this with 92 and go through the whole process, you can solve for T now. And you can do that for any point in time, or for any temperature, right? So to find T when we found them, we solve this. 92 is their temperature, equals 72 plus 26.6 e to the negative 0.0813 t. So we've already done something like this. I mean, we've moved things around, so let's do this again. We subtract 72 and get 20. We divide by 26.6, right? Remember, the left side is the temperature of the body at some particular point in time. We want to know when we found them, right? What was their temperature when we found them? 92? So we want to know the time that corresponds to finding them. Remember that before we didn't know what K was, right? So we couldn't have ever figured out what T was if we didn't know what K was. So we found K first, and now we're going back using K to find T.
But in order to find K, you had to have a second measurement.
That's right. We had to have two measurements. You could not do this. There's no way to just walk in the room, take the temperature, and go, okay, temperature. That's not temperature. Take the temperature, right? However you take a temperature, just with that little laser thing, right? But whatever. You take temperature, and that's not enough. You need to know another data point in order to figure something out, which isn't difficult to do, right? You just wait for a little while. Okay, so subtract and then divide, you get the 0.7518, something like that, 19. What did we put, 8 or 9 earlier? No. 0.752 is what we put? Okay. That's what you get when you take 72 away and divide by 26.6. And we still have on the other side e to the, bless you, negative 0.0813t. Yes? Subtracted and divided. And now I'm going to have to play the same game again to try and get that t out. Natural log on both sides. Natural log 0.752 equals natural log e to the negative 0.0813t. You can drop this out front, and what's going to happen to the natural log e? It's going to go away. So you have the negative 0.0813t equals, on my calculator, I'll go ahead and do this natural log. Natural log of 0.752. I'm getting negative 0.285. And finally, take that and divide it by negative 0.0813. And you get 3.51 approximately t. There you go. What does that mean? 3.5 hours. The body's been there for 3.5 hours. So they're ready in Laredo, about to cross the border, the perpetrator, right? They're already gone. They're out of here. Houston, yeah, depending on which way they're going. Understand? That's a pretty involved problem, but that is a real life applicable problem. I mean, that's not, you know, that's something that you could actually do. And I'm not suggesting you test this at all, you know. Now, another thing that we could do to kind of get an idea of what was happening here, I'm going to graph this exponential function for us. What was it? After we found k, it was 72 plus 26.6, right? E to the negative 0.0813 t, right? I'm going to use x here. And then this, and then graph it, and then let me change my window, my zoom here, my view. I hope this works. Okay, this is a pretty good, I think that might be a little too far out. All right, I think that's good. All right, I hope you can make sense out of this. Time, this is time on this axis, and this is the temperature of the body. At the time, the moment the person was killed, or died naturally, whatever happened, their temperature was what? 98.6, which is up here, right? And then this is the model of the dropping of their temperature with respect to time, right? Using the exponential function. Now what's happening is that their temperature of their body over time is getting closer and closer to what? Room temperature, which is 72 degrees, right? We walked in here and we didn't know what time it was, right? We just walked in and we knew it was, their temperature was 92 degrees, somewhere around here. Later on, we measured their temperature again and we saw it was something else. We used those two data points to be able to actually construct this thing. And then now we can go to any point in time and figure out, you know, we could figure out the temperature at any point in time, and then, or someone could give us the temperature and we could go back and figure out when it happened, which is what we did to figure out 3.5 hours. So, okay, that's just a visual representation of what's happening. Now, there are some other problems, word problems, that we can talk about. I said I wanted to do at least 2, right? I said that last time, or was it 3? Right. Was it? Okay. So there was a review that was handed out, right? Or sent out. And I'd like to discuss this half-life problem. Okay. So when it comes to half-lives, we have not talked about half-lives yet, right? We have not talked about it. I mean, it's in terms of I haven't given you a formula or anything like that, have I? So I would like to follow the book here. So let me use the same variables and stuff the book does. Okay, so this is the problem that we're given. The half-life of a certain radioactive substance is 20 hours. Wow. That means remember when I was tearing that sheet, took the sheet, I said, here, you got this substance. In so much time, half of it goes away, and then half again, then half again. This one, every 20 hours, half of it's decaying down, all right? How long does it take for this substance to fall to 15% of its original value? So we have, you start out, we've got this stuff, there's 100% of it there, right? That's happening at the very beginning. Time is 0, right? That's the idea. At t equals 0, all of it's there. Then, half of it decays, so half of it goes away. So now you have 50% of it there, right? How long did that take? T is now what? 20 minutes. So this is measured in minutes. Just keep that in mind. Is it hours? Yeah, sorry. Hours, right? If they said days, then we would be thinking days. If it was years, we'd be thinking years, right? Just depends on the problem. That says hours. Can't tell. Okay. And then again, it would decay again. Half of it would be there, right? 25%. Half of 50 is 25. And that would be T is what? 40. What we want to know is when will 15% of it be there? Understand? I can tell you that 40 hours later, 25% is there, but when exactly will 15% be there? So here's what we will need in order to do this problem. We will need to know what formula you use. Uh-oh, where'd it go? What formula you use for something like this. So here's what we use. And this is out of your book. For radioactive decay, you know what, I think I'm going to switch back to our lecture notes. Here we go. So radioactive decay. We have the following. A of t equals A sub 0. How else do we say A sub 0? A naught. Like you tie a knot in a rope, right? Or you tie a knot in a shoelace. A naught. Okay, with K being a negative number. This is the model for radioactive decay. Now let me explain what all the variables are again. T is time. That can be measured in years, hours, seconds, milliseconds, right? It doesn't matter, but you'll know that somewhere in the problem. K is your decay constant. In other words, the K is dictated by what it is that you're looking at. If it's uranium versus some carbon-14, just depending on what it is, they decay at different rates. This K dictates that rate. So that will change from substance to substance. The E, of course, is just a constant. We don't need to talk about that. The A naught is the amount present at the beginning. Or starting amount. So that's what when I'm saying starting amount, I'm talking about how much of the substance was there to begin with. So you could say 100%, right? But you could also say 40 pounds, right? It just depends on how you want to say it. If you want to look at it in terms of percentage versus weight or mass or something like that, that A is just a measurement of how much is there. Now, why is it the original amount? Because what happens at time is 0. When I plug time 0 in here, this is 0. What's e to the 0? 1. And so this is just A naught. So at the beginning of time 0, you're always going to get that number. A naught will always be the starting amount. Then from there on, it's going to decay down. All right? Now, A of t is the amount present at time t. So the left side of this function, what comes out of the function's value, it gives you how much of the stuff is there after a certain amount of time is transpired. Understand? We okay with this? The fact that the k is negative means that this exponential function looks like what? Remember, there's two types of exponential functions. We have growth and we have decay, right? Those were the two kind. When you put a negative number up here, it looks like this. E, let's just make a negative up. How about negative 2t? We need to understand that this is decay. The base of this is E, right? The base is bigger than 1? I thought I said that if the base was bigger than 1, we had growth. I did say that. Didn't I? Of course I did, yes. So why is it decay? I'm telling you it's decay. Because the exponent, what does putting a negative up there with the variable do? What does a negative out front in front of everything do? Think of transformations, up, down, left, right, flip. A negative out front flips it over the x-axis, right? What does a negative up near the variable do? Flips the y-axis. So we actually do have growth, but the negative exponent flips us over the y-axis, so it's just like this, so now it becomes decay. Do you all understand that? Now, I heard it flips as a fraction. Who said that? That would also, you could look at it that way also. But I'm going to use the reflection idea. Okay, so let's go back to this problem. That's the model we're going to use. Where the heck is it? A negative just out in front of everything. Like if I have e to the x, it's going to look like this. If I have negative e to the x, it's going to look like this. A reflection over the x-axis. But if I do e to the negative x, it's going to look like, oops, I missed the, it's going to look like that. It's the black one here flipped over the y-axis. See the difference between all those? Nope. Not with the exponential functions. Okay, so here we go. This was our problem, right? We were trying to figure out how much of this stuff was there. So let's use our, let's write down the model. Do we know anything here? Half-life of a certain radioactive is 20 hours. How long does it take for this substance to fall to 15% of its original amount? remembering that we're going to use this model, we need to come up with K, right? We need to find K so that we know the decay constant for this thing. How am I going to do that? What do you know about time? 20 hours. But that would, so you're saying I should plug 20 in here? Okay. I'm trying to get you all to see this. 20 is right to plug in 20 for t, but what is it about 20 that we know? That's only one point in time, right? 20 hours. So what happens if I plug in 20 for t? How much should be there? Half of it, right? Half of it. How much is there in the beginning? We don't know, but would you agree if we look at it in terms of percentages, 100%'s there? Yes? And so if I know the original amount is 100%, which I think I will convert to a decimal. How about 1? 1 is 100%? Yes? Then I know that at t equals 20, how much should be there? The amount there should be equal to half of that, which is 0.5. Agreed? That's how I'm going to use the 20. I know that when I plug 20 in here, this is going to be 1 always, right? That was the original amount. But I know that when I plug 20 in here, this is 1, and this side has to be 0.5. So I'm using that condition that half of it will be there in 20 hours. So this means that if I take the left side is 0.5, half of it must be there when I plug in 20. Look, this is critically important that you understand where this is all coming from, because you do every half-life problem like this to try and figure out K. That's why knowing the half-life of something is so important. If you know the half-life, you can find the K. And here's how you do it every time. The original amount, 100%. The left side is how much is there after a certain amount of time. Well, we're doing half-life, right? Half-life, half of it's there. How much time does it take for that to happen? 20 hours. Make sense? If this had been a different material and the half-life was 10,000 years, you would be the same setup, except this would be what? 10,000. Okay? So every one of these half-life problems is going to be set up the same to get K. Now let's actually get K. I don't need the 1 there, do I? That was just to help you see that's 100%. And K times 20 is 20K. How do I get K out of there? We have to bring natural log in on both sides. Natural log 0.5 equals natural log e to the 20K. But natural log of e to the 20K is just 20K at the end of the day, right? After we drop it out front and get rid of the natural log e. You have to figure out what natural log of 0.5 is? Yes, ma'am.
I have a question.
Yes.
I did another one similar to this one,
Mm-hmm.
and I actually just put ln, 0.5.
Uh-huh.
I just left it like that, or can you put in the calculator ln? Yeah, and then just give.
Like do this on your calculator?
Yeah.
Yes. Yeah, you're going to want to know what K is. So it's best to get K as a decimal. You don't want K to still be like natural log of 0.5. You're saying leave it like natural log? If we're going to come back here and plug K in to this formula, then let's figure it out as a single decimal. Okay. So do this on the calculator and then divide by 20. All right. I'm getting negative 0.034647. This is where I'm going to want you to go at least 3 decimal places, all right? If you go 4, I'm not going to get upset. If you go 5, I'm not going to get upset. Just you can't round that to 0.03. We need a little more than that. 0.035 would have been fine. Equals K. So this is This is it. I mean, this is the grand finale of this, is that if you have, for this particular substance, we have this formula. Right? The amount that will be there will be equal to the original amount, which was a 1, e to the k, which we just found, times t. Now, let's answer the question. So you have to always come up with the function first, then you can answer the question. So what is it that we're asked? How long does it take for this substance to fall to 15% of its original value? So we want 15% of it to be there, right? Which means I want the left side of this to be what? 0.15. So you're going to plug in 0.15 here and solve for t. And you'll be done. Which, let's do it, right? I'm going to push it right in here because I'm out of space. So how long until 15% means we want 0.15 to be equal to e to the negative 0.0347 t. You do natural log on both sides again. And the same thing will happen. The exponent is just going to drop out. The natural log of e is going to cancel. Do that on your calculator. What do you get? Natural log of 0.15. Divide that by a negative 0.034. Yeah. Should be bigger than 20. Should be bigger than 40. Negative or positive? 54.0203, something like that. 20. Okay. What do you have? 54.20. Okay. 54.2. Good enough. Approximately t. Anyone else get 54 point something? 54 point something, we're happy? You need to be able to get that on your calculator, okay? Now, think about your answer. Does it make sense? It took 20 hours for 50% to be there. It took 40 for 25%. Does it make sense that it would take 54.2 for 15% to be there? I think so. I think that makes sense. Because how much would be there after 60 hours? Half of that, right? 12.5. So it shouldn't quite be 60 hours. It's exactly 54.2. This is how they, well, there's rounding issues on everyone. It depends on where you round. If you get 54 point something, you're okay. If you're getting like 72, something's wrong. You got 54 point something? Okay. So there is a particular what is it? Carbon 14, right? So carbon 14, is that one of the problems on here also? No. Okay. So carbon 14, there's two types of carbon 14, and it's in your body and my body and all living things, right? We have two types of carbon 14, and they're the same level. When we die, one of the levels of the carbon 14 starts to drop. The other one stays the same. Okay? And so what happens is, you're dead and your carbon 14 starts to deteriorate. It's exponential decay. So if you go find a body that's been, in the woods buried for like thousands of years, you can't take the temperature anymore, right? I mean, because that law of cooling is only good for like the first few hours, right? It's once the body reaches that temperature of the room, you can't go back, all right? Does that make sense? Right? If I come in and the body is 72 degrees and I need that second data point 2 hours later, what's the body going to be? 72 degrees. So there's no second data point to get. Does it make sense? So you keep throw out Newton's law of cooling. So we find this bone. What we do is we measure how much of the carbon-14, how much of the stuff that doesn't go away is there. So let's say I'm using made-up stuff here because I don't know enough about carbon-14 to be able to speak factually. But I will say, let's say there's like 10 grams, or let's say 1 gram, just to make it easy. 1 gram of carbon-14 that doesn't decay. And over here, when we measure it, it's like 0.03 grams. So they've lost a lot of the carbon-14. That's an exponential decay model. That's exactly what we were just doing. And so what you're able to do is you're able to use the half-life of carbon-14, and so it's not 20 hours. It's, I think, half-life of carbon-14 is like, I don't know. Someone get on your phone. I know you all can do this. Someone who has their phone real quick, just do half-life carbon-14. You have my permission to use your phone. Okay. Let's see. What's that? Damn it. 60? 5,760? 30. Okay, I was going to say 5,760, but it's been a while. Okay, so if you have this, let me get back to our notes here. Years. So for carbon-14, the half-life experimentally. You measure it, you let time go by, you measure it again, just like we did with the body. 5,000, but you don't need to. Like, you know how we waited 2 hours for the body to cool? Same thing. You don't have to wait the full half-life. Right? Like, I didn't wait for the body temperature to drop by half. I just waited till it dropped. So the same process would be used. 5,730 years is how long it takes for half of it to go away. All right? So let's say we have this. This is another example. You find a bone, and it's lost 87% of its carbon-14. How old is it? Now, these are approximate ages, right? It's not going to nail it down to like the exact hour, okay? But when you're talking about things that are like 40, 50, 60,000 years old, 100,000 years old, if you're off by 10,000 years, you're off by 10,000 years. You know, it's close enough to say it wasn't yesterday, wasn't last year, wasn't back in the 60s. You know, you can like narrow things down. Okay, so how old is it? Well, let's first realize this is decay, right? So we know it's got to follow this. KT? We've got to figure out what the decay constant is. How do we figure out the decay constant? If someone gives you the half-life. This side becomes 0.5. This is 1, right? And then e to the k times t, and t is always the half-life they give you. So 5730 k, right? Do you now see what I mean by once they give you the half-life, you can always come up with your decay constant? Okay. One is saying that there was 100% of it there to begin with. The 0.5 is saying half of it's going to be there at this point in time. How long did it take? 5,730 years. So go ahead and do this. You're basically going to be looking at natural log of 0.5 equals 5,730k. I'm getting negative 0.000120 9681. Anyone else get that? Approximately, K? Now, would it be wise to round 3 decimal places here? No, because you would just be putting 0, right? So this is where accuracy matters. In a problem like this, you would want to go as far out as you possibly can, because this is a tiny number, isn't it? This is a tiny number, 0.0001209. So I'm just going to use everything my calculator gave me. Did anyone else get something close to that? Yes? We're good or no? No? You didn't? Is it giving it to you yes, it's given to you in scientific notation. The e to the negative 4 means move the decimal point over 4 places to the left. You got the same thing? If you don't like that, you can turn that mode off. If you'd prefer that it spit it out the other way. Do you prefer it the other way? You just go to mode. Let me see real quick. Mode. You're in normal mode. Yeah, your menu's different than hers, though. Yours is all fancy. Not to say yours isn't, but yeah. Try it again. See what happens. I don't know if that fixed it. Okay, but anyway, what we know now is that A of t equals e to the negative 0.0001209,681. Did it do anything or no? Didn't? Okay. It's going to be a big problem. Yeah, because if you put 1.2 in there, negative 1.2, it's way off.
But if we went times 10 to the
But you wouldn't want to put that up here like that. No. That's bad notation. That's like putting two commas or something. It's, you know. But if it's the only number, see, it's a power up here. It just looks kind of weird. I mean, I'm not going to take off for it. It's just like, don't use the little e though. That's your calculator's notation. That's not mathematical notation. If you're going to do it, you have to do times 10 to the, yes. I'm going to get to these. I'm trying to get through this right now. This is our thing, right? We need to now figure out how old the bone is. So find a bone and it's lost 87% of its carbon-14. How old is it? So what am I going to do with this? What do y'all think? 0.87 equals that? 0.13 equals that? What do y'all think? Let's take a vote. We're trying to figure out how old the bone is. It says the bone is, you find a bone and it's lost 87% of its carbon-14. How old is it? We've got the function that dictates what happens, but I need to replace the left side with how much. So what does the left side represent? How much is there, right? How much is there? If it's lost 87%, how much is there? 13%, which means 0.13. I will trick students on a test that way. Not intentionally, because, I mean, that's the way they appear in, real life problems. You're like, okay, we've measured how much. You have to know how much they've lost, how much it's lost, how much is there. Know the difference between the two. So this left side is actually 0.13, 13%, which is what happens when you take 87% away from 100, equals e to the negative 0.0001209,681 t. Natural log, divide through by this thing. I'm going to let you do that on your own. Anybody want to venture their answer out here or throw their answer out here? Next. 16,000. 15,000. 866. How many decimals did you go out? Okay, you did like when you did this. Did you go pretty far out here with this?
I did
All of it, right? Someone who got 15,000. Did you use all these numbers also? Yes? Try it again. Something was off there. You should get 16,865.8 or something like that, approximately T. Yeah. So it will depend on how much you round this by. Here's my recommendation is on the test. If you're going to round this, and that's what you're going to type into your calculator, show me what you rounded to. Like when you come over to this step and you do the natural log of 0.13 divided by, if you round it to 1209, if that's what you stopped at, then write it down so I know that you're going to be different. Your answer's going to be different than mine because where you stopped. All right, just make it clear. So the bone is about how old? 17,000 years old. Okay? Make sense? Now, what were you asking? Number 25, what? On the review?
yeah.
Okay. I think that is good as far as the stuff, exponential applications. So I am going to choose to not do logistic. So number 25, I'm not going to do these. Okay, this is a different model. Look at this model. Right here, this is the model function. We have not talked about it. I'm not going to talk about it. Is that okay? What? No. I will not ask you logistics. Remember I said there were a few different applications. There's like bacteria growth, right? Decay. There's Newton's law of cooling. You all picked Newton's law of cooling last class. I've shown you decay, right? So, well, let me go through these. I'm just saying, addressing number 25, don't worry about 25. Well, let's talk the review now. We have 40 minutes. Let me talk review, all right? Because in the email I said that this is a review that one of my colleagues uses, and that by no means is this the review that I would have necessarily came up with, but it is a good, I think it's a good review. It's, you know, if you can do this, you'll be fine. So let's talk about it. Y'all ready? I know a lot of you don't have it in front of you. That's okay. I've started doing it, and I haven't finished it. What, the answers? I don't know if I'm going to have the answers, but let's talk through it and see. I'm going to try to get them done. All right, I need to erase some of this because you can't see what I'm doing. Okay, first question. Determine which of the following functions are exponential. If it is exponential, determine if it's growth or decay. This is very much connected to what I just wrote here on the board. This is an exponential function because you have a base 4/3 raised to a variable power, right? So the variable is in the exponent. Your base is a number. That's an exponential function. Now, the base is bigger than 1, which normally means what? Growth, right? But I've got a negative up in the exponent, right? I can't do that without covering it up. A negative up in the exponent, which flips it over the y-axis. So I even put here, reflected over the y-axis, exponential, it's decay. See it? Okay, this one, is that an exponential function? No, it's a log function. Is this an exponential function? X to the pi. No, because the base is the variable, right? X is the variable in the base. For an exponential function, you have to have the x up in the exponent. So that is not. This one, yes. What is the base of this one? 1/2. Remember, the 100 cannot touch this. This cannot become a 50 because you have to do the exponent first. It's implied that this x is on the entire thing. Actually, it's kind of bad notation here. It should be parentheses around this whole thing, right? Because you could think that's 1 to the x. So we'll say the base is 1/2, which is what? When the base is less than 1, what do you have, growth or decay? Decay, right? But do we reflect over any axis? No, right? So this is just decay. This one, e to the 5t. Yes, that's exponential, but the negative exponent gives me reflection over the y-axis, so it's decay again. But only because the e was bigger than 1, right? So what would this be, growth or decay? If I gave you this function, that would be growth. Because 1/3 means decay, right? So it looks like this, but then the negative exponent flips it over the y-axis, so now it's growth. So you have to look at both things together. It can't just be one. That is like saying 3 to the x, exactly. Because remember, negative exponent, you flip it, the fraction. So that is exactly the same as 3 to the x. So it should be growth, shouldn't it? Okay. All right, next one. I like this problem. I never gave you anything like this, but I really did like this problem. So let's go through this. I can't tell you. You're asking me to tell you if I'm going to give you this. I can't tell you. Look, this is a review, right? This is conceptual. This is a very conceptual problem. I never asked you to do anything like this in class, right? It's whether or not you can connect the ideas. What does f of g of 6 mean? It means 6 goes into what first? The g function. And then that answer goes into what? F. So I'd like for us to plug 6 into g. So here are the graphs over here. G is this red one, right? That's G. And then F is this blue one. Right? That's F. So first plug 6 into G. What happens when you go to the red one and you plug in 6 for X? What does it spit out? 5. Do y'all see that? 6 goes into the G function, it spits out 5. That's what's sitting in there, right? Plug in 6 to G, it spits out 5. Do y'all see it? Now take that answer and plug it into F. So now go to the F function and plug 5 in. And what does it spit out? 1. Do y'all see how that works? It's like a chain. Once you see it, it's not that bad. Okay, 6 goes into G first. Okay, so let's go to 6 on the x-axis. Let's plug it into G. Plug into G, which is the red one. Plug in 6, it spits out what? 5. Now take that answer, 5, and now plug that into F. So go to 5 on the x-axis, plug it into F, and what does it spit out? 1. No? The answer from this 5 is now going into F. So just forget that G was even there. Just plug 5 into F, and what do you get? 1. Got it? This is like one of those light bulb problems. It's like on or off. Once you see it, it's there. Until you see it, it's black darkness. Okay, what about this one? G of G of -1 means -1 goes into what first? G. So go to your G function, plug in -1. What does it spit out? Spits out 3, doesn't it? Yes? But now take that answer and plug it back into G again. So now you go to the G function, you go to 3, and you plug in 3, and you get 1. Do y'all see how this is working or not? Okay. All right. What is F inverse of 3? F inverse means you're looking at the y value. You're trying to figure out what x value it came from. So go to your F function and look at where the outputs. Here's my F function. Look at where the outputs, the y coordinates. Where is the y coordinate 3? Right there, right? The x coordinate, right, that I plug in 7, it spits out 3, right? So the inverse should take 3 back to 7. Does that make sense or not? F The original function f takes the value 7 and maps it to 3. Takes the number 7 and sends it to 3. That's what f does. The inverse should take 3 and send it back to where it came from, back to 7.
So, okay, f inverse of 3.
Mm-hmm.
We don't look at that. We look at the point in the graph.
You're looking at the y coordinates.
Yeah, exactly.
Yes.
Yeah. Okay.
But only because it's the inverse function.
Okay.
Okay? If that said f of 3, you just look at 3. You'd go out here to f function, you plug in 3, and, well, it's not even, it doesn't even show you what it is at 3. But okay, this one right here does not have to be difficult. Okay? F of f inverse of -1 is -1. Why? Because the inverse and the f, they kill each other off, don't they? The whole point of this is that you plug something in. The property of the inverse is that f of f inverse of x is x. Right? So these are gone, you just get -1. So if I put here f of f inverse of a red cat, you would put red cat. You know, it doesn't matter what's here. Because the inverse and the, yeah, they cancel. If you did it, now look, let's do it. You're plugging, well, no, because we don't have the inverse function up here. Well, we could. First thing you would do is plug -1 into the inverse of f. So you go to f, you figure out where the y coordinate is -1, which happens here at 1. So then you take that answer and plug it into f. So plug 1 into f, and what does it spit out? -1. So you're back where you were. So it's weird, but okay, let's move on because time. These I won't work through all of them. I just want to talk through them because I want you to do them on your own, and then I'll provide you answers later. Okay, for functions f and g, find f of g. So this is where you had to take this g function, plug it into f. Remember, we get these complex fractions. You've got to get common denominators. Remember all this? Okay, you had a quiz, and I think you had take-home homework. I'm sure you had homework on this. Now, the domain. Remember the chain that I showed you in class. X goes where first? To G, and then that answer goes to F. So you look at what are the restrictions on G. What can you not plug into G? Here's G. What can you not plug into this? 5, right? So I throw 5 out. Now, what can you not plug into F? 3. But remember, G's going into 3, right? So I ran out of room here. I need to make sure on this little link right here that the G function cannot be 3. Right? If this thing ever spits out a 3, I'm in trouble. So you have to go solve that. Multiply both sides by 5 minus x, and you figure out eventually that x can't be 15/4. So your domain is this. You take out 5, you take out 15/4. Yes. I'm not a big fan of this problem. I did it anyway, but I wouldn't spend too much time on it. I'm going to try to. I don't have all the answers done yet. Look, if you're asked to sketch this function, you have to realize that this is an exponential function, -3 raised to the x plus 1. You know what 3 to the x looks like. It's been flipped over the x-axis because of the negative out front, so here's the flipping of it. And then the whole thing's been moved up 1. So the red one is my final answer. So I gave you like a take-home problem, I think, where you were supposed to graph these. And the other one, again, I'm not such a big fan of because sketching the log function is not a big deal to me, but I did it anyway. First, I sketched 3 to the x because that's the inverse of log base 3. So remember, we do that, make a table, then we flip over the x and y coordinates. That would be the graph of log base 3. And then the rest of it is just moving it around. This thing moves to the right 5. I would just not focus your attention on that, okay? Don't worry about that. look at the next page. Fill in the blank. The domain of an exponential function is all real numbers. The range of a basic exponential function is from 0 up, right? Not including 0. The domain of a log is the opposite of what the exponential was, right? The domain of the log is the range of the exponential. The range of the log is the domain of the exponential. So they just switch places, don't they? Okay. Logarithms are exponentials. Again, this wasn't my test review, and so I wasn't quite sure what some of these things can be left to interpretation. Logarithms are exponentials. Remember we talked about logarithms and exponentials? They're all the same thing, just a different way of writing something. Okay? So it's just a different form. Exponential and logarithms are inverses of each other, right? Exponential functions can be used to model growth and decay. Logarithm functions can be used to model, and I left it blank because there's so many things that can be used to model. I wasn't sure exactly what this instructor wanted to say precisely, so I left it blank. I'm not going to ask you that. Exponential functions have horizontal asymptotes, right? Remember these horizontal asymptotes for exponential functions, and it's the opposite for the log. It has a vertical. I like this problem. Given the one-to-one function below, find the domain, range, and inverse. I don't like this problem, but I like this one. Only because I didn't give you a problem where I restricted the domain. Yes? Yes. Okay, so check this out. Let me explain what I'm doing here. Here's a function, right? I want the domain, range, and inverse, right? The key to this problem is this. Remember that if you have a function, it has a domain and range, right? The inverse of that function, the domain and range flip, don't they? So if I'm trying to find the domain of this function, what can you tell me about it? It can't be what? -1. So that's domain, no problems, right? To find its range, you actually just need to go look at the domain of the inverse. That's what you need. So we're asked to find the inverse. How do we find inverses? Change out, y is equal to the function. You switch y and x. Then you solve for y. And remember I promised you it would be this ugly one where you have to move it to the other side and realize that you can get all your y's on one side and factor out? Go back and look in your notes. It's going to be like that. This is your inverse function. So the inverse function is this. I've answered what the inverse is. The domain of the original function you said was x could not be -1, right? I put that here. I was running out of time. But why did I say that the range of this function is everything but 1? Because it's the domain of the inverse. See, look at the inverse function. What can x not be? 1. Yes or no? I mean, y'all need to let me know. Yes? Okay. You're good? All right. So that's the way I would do it, is don't go try and figure out what's actually, like, what the range is. Just go find its inverse's domain. And now you have the range of the original. So I should put, for clarity here, the domain of f is this, the range of f is that. All right, so I like that problem. And then I think this is where I ran out of time. So let's see what else I've got here. Find the functions f and g so that f of g of x is this. I don't recall doing that. Yeah, I will omit that. You'll talk about that again in calculus, and that will be important to be able to break a function down into smaller pieces. But I think once you get to calculus, you can pick that up pretty quickly. I've never had cal students have trouble breaking down a function like that. Okay, find the domain of each function. Very good problems here. The domain, remember the domain of a log. You need this thing inside, which we call the argument, had to be what? Greater than 0. This is what type of thing here? A quadratic inequality. And the way that we do this is tricky. This will be the second test that you've had quadratic inequalities on. One of the ways you do it, you find the x-intercepts and you draw a parabola and you're trying to figure out where it's above the x-axis. Okay? We've done it. I'm not going to go back through this. You can go through my videos. You can go through the notes. I've done quadratic inequalities already. Here, this one, the argument, again, must be greater than 0, right? This is a rational inequality. And the way we did this was to look at it like set the top to 0, -2, set the bottom to 0, 5, draw those, take test points, answer whether or not it's bigger than 0. You just have to be careful, you know, don't include 5, don't include -2 in your answer because that makes it 0. Again, we've done this before, so I'm not going to redo them today. Write in expanded form. What this means is to use all those properties of logs. So let me work through this one. Do you see that I have something divided by something? Yes? So I can go log base 5 of cube root of 5e minus log base 5 of, and then I got a bunch of stuff down there, x squared times x squared plus 4. Yeah? That's the first thing I'm doing. How about this? What can I do with this? I could make that a 1/3 instead of a cube root. Is that all right? Then what can I do with the 1/3? Pop it out front, right? So I can do 1/3 log base 5 of 5e minus, now what are you going to do with this log over here? You can split this into 2 logs, right? Multiplication inside of a log becomes 2 logs being added. But what about the minus sign? It's got to go both. So it's going to become log base 5 x squared. It was plus, but now it's minus. Log base 5 of x squared plus 4. And I'll put parentheses around this x squared too. Can I bring this 2 down? Yes. Can I bring this 2 down? No. Can I break this apart anymore? No. This one's done. This one, the 2 can come out. This one, you can actually split that up into 2 logs. Right? Those 2. What's log base 5 of 5, everyone? 1. 5 to what power is 5? 1. So this is just 1/3, isn't it? 1/3. This one you can't figure out as easily, so we'll just leave it, right? 5 to what power is e? I don't know. Bracket? No. You mean like put a big parenthesis around that? No, because I distributed the minus sign through already. You see? This minus sign? This would have split into 2 and would have been a plus, but then I would have passed the minus sign through. So 2 log base 5 x minus log base 5 x squared plus 4. And that 1 out front, right? This is a 1. This is in no way a solution. I'm just thinking through this, talking through this, being sloppy. Now this one is the opposite, right? Now you want to put these together. So I probably put the 4 up first. What's ln of 2 to the 4th? Natural log of 16? So this is natural log 16 plus natural log x. Do you want to put these 2 together? -2 here. If I have natural log of 4 plus natural log of this, I can put it into 1 log, and I multiply the 2 together, right? 4x plus 4. Or you could do 4 times x plus 1 in parentheses. Now I really don't even need the brackets anymore, do I? So how about the 2 up in front? Put it up minus natural log 4x plus 4 to the second power, so the 2's coming up. Just got rid of the brackets, right? Didn't need them, so they're gone. So that 2 is going to come up here. Can I do anything else? Put these together. That's natural log what? 16 times x, right? Minus natural log of 4x plus 4 squared. Can I put those together? Yes, subtraction, right? Natural log, subtraction is division. That's done.
Back at 10, you put like 1 and 6. For the 1/3 of log of 5 and 5, you just put 1?
1/3. These two together would become 1/3. 1/3 times 1. Yep.
When you're doing the adding and subtracting of logs, they have to be anything order. You can't like take like regular addition and subtraction. You can just do willy-nilly. You can go from backwards and forward, but like you can't just say like natural log of 16 plus and then put in parentheses natural log of x over natural log of.
You mean like do these first?
Yeah.
You could have done it.
You can do it that way.
You could, because this would have turned into natural log of x over this, right?
Yeah.
And then when you put that together with this, you would have multiplied a 16 through, and that 16 would have joined the x that was on top. So it would have worked. It's just a little tricky. Sometimes, sometimes that can be a little dangerous. I like to work left to right. Solve this equation. Loop-de-loop time, right? A to the negative 3 is 1 over 64. 64 is 4 cubed, isn't it? This is 1 over 4 cubed. 4 times 4 times 4. But that's the same as 4 to the negative 3, isn't it? So what must A be? A must be 4. A is 4. Ooh. Ho, ho, ho. It looks like too much. This is 27x squared plus 7x. Property of exponents, right? Same base on the left. Add the exponents. I'm going to on the next step, I think. That's what it doesn't matter, no. What about the right side? Is it okay to write that as 9 to the x minus 3? Because that's what it means, right? Now, we're back to a problem that we did right in the beginning when we were first learning about exponents, is where you try and get the same base to the same power and you match up the powers. We need to get the same base here. So what base is a common? 27 is not 9 to a power, though. 27 is 3 cubed. And 9 is what? 3 squared. Right? So now you have to do 3 to the 3 to this. You multiply the 3 through here, right? So you get 3 to the 3x squared plus 21x equals 3 to the what? 2x minus 6. Do you have the same base? Okay, you set these two equal. That's a quadratic equation. When you set those two equal, it would be a quadratic equation. You go solve that, right? Do you need to check your answers? It's not a log equation, so you don't have to. Although it's good to check to see if you get the right thing, right? A what? It'll be a quadratic trinomial once you move everything to one side. Yes? You get two solutions? Possibly. You could have one, you could have none. Just depends. Well, you could have like a repeated root. Like you could have a repeated solution. Like a repeat. With exponential functions, it would be, you don't have any domain restrictions. So you don't, it's going to work because you didn't do anything weird like square both sides of an equation that creates extraneous solutions. So they should both work if there are two of them. All right, next one. Yeah, this one I would just get away from the whole matching basis thing and just go to what we know. I mean, go with the big powerful thing, which was you're trying to get an x out of an exponent, right? Then start coming in with the log, but you got to get rid of the 5 first, right? So make that a 50? No, don't make that a 50, right? If you don't want to get any points, make that a 50. Right? You cannot do that operation first. Divide by 5 first. Now, natural log both sides. You could do either one. Either one. No. Did everyone see what I did there? No? Yes? Divide by 5. Take natural log on both sides. Drop the 2x out front. Trying to get x by itself here, I'm going to divide both sides by 2 and natural log 10. So x is equal to natural log 3/5 over the 2 and the natural log 10 that I need to figure out on my calculator. I'll do all that and give you the answer. That way you have you know what it is. Haven't I answered that question already? Like 3 times I think I've answered that question. What did I say? I don't know. I'm going to try to. All right? I'm giving you as much as I possibly can without handing you a test. I mean, remember, this is about preparing you for the next math class, right? You need to get used to having less and less of a crutch to hold you up during a test. It's got to come down to you and understanding the concepts, not just, oh, there's a problem. I just need to be able to do that type of problem on that test. And then when the test is over, I'm not going to remember any of this, and who cares, because I got to be in the class. That's not the approach. The approach is understanding it to a point that the review guides you through this, right? But just shut up, Robert. I didn't finish. Yes, I did. I got negative 0.111. Yes, you would. Okay, that is the correct answer. Make sure you get that answer on your calculator. Don't let it be the test, remember? Don't let it be the exam is the day that you're learning how to use your calculator for the first time, right? I'll have no compassion when you bring that to me. I don't know how to use it. Go sit down. I won't even talk to you about it. Don't ask me to use your phone either.
Doesn't matter whether we go to 3 or 4.
No. What did you do to it?
No, I did nothing. I just sometimes I mess with it. And
if your calculator is completely acting buggy on you, you can bring it up to me and I'll do a whole system reset on it. But other than that, I mean, yes.
How do you put it in? Put that to the calculator?
That's what you have to figure out. That's right. Okay, so you need to, but your calculators are different, so it's not going to matter. Your calculator is different than his, right? And that's what I've been telling you about bringing your calculators so I could help you learn how to do these keystrokes, right? You need to be doing the natural log of 3/5 first. The 3 and the 5 have to be in parentheses or have to be grouped together. I have to help you on your specific calculator, but I'm not going to stop the review right now to do that. I'll help you after class. Okay? But let's make sure that you get to this answer, all right? Next. How would you do this? Oh, we talked about this last class. This was a squinting of the eyes problem. Oh, this is a classic problem. I mean, we love these problems. I don't know why. We just love them. Do what? 2 to the third. But none of our bases over here are 2. Why do I do this? Uh-oh. We did this last class, didn't we? Oh, I know I did this last class. That's right. This is a substitution. You're rewriting this, and you're realizing you have 5 to the x squared plus 2 times 5 to the x equals 8. Well, let's move the 8 over. Minus 8 equals 0. Do you see you have 5 to the x here and here? You replace that with u, and now you have a quadratic. Please reference the notes from last class. I don't remember. Were they not there? Look at this is a perfect example right here. 4 to the x minus 2 to the x. See, I did one just like this. Go watch the video, make the substitution, solve the quadratic, check the answer. Wait a minute. Hold on. Where the hell is this? I'm lost now. Sorry. There it was. What do I what now? That's going to become 2u. This is going to be u squared plus 2u minus 8 equals 0. Okay, I've got to keep going. We only have 7 minutes left. Log equation. Well, I did these also. You got to put these two together first. Right? You got to bring that 2 up. So it'll look like log base 3, 4 minus x squared equals log base 3 of 4 times this. So 52 minus 8x. Now, if I have log base 3 of something equals log base 3 of something else, you put those two equal to each other, don't you? What type of equation would this be? Not quite linear, because that thing is squared, isn't it? So you'd have to FOIL this out. 4 minus x times 4 minus x. Distribute it all out. It would be a quadratic. You move everything to one side, you solve for x. Then check your answers because it's a log equation. Well, if one of them is not correct, I'll take something off. Remember how to check them. You just plug them back in here real quick and you see, make sure you get a positive number. Right? That's all you have to do. How about this one? Put them together. Left side becomes, oh wow, look at the exponent, or the base is x. Huh, weird. So you put them together. This is what, 12x minus 20 equals 2. And now, oh, okay, I see how this can work. Loop-de-loop time, right? Here. X squared equals 12x minus 20. Another quadratic equation to solve. Where's the what? This loop. Remember the loop, right? So it's x raised to this. Why did I not do the loop on the last problem? Because I had logs on both sides. Right? Logs on both sides, you just set the insides equal to each other. This one, I only had a log on one side, so I used the loop. Population. We didn't really talk about this. 19. This is the change of base formula. Very simple on the calculator. Right? Evaluate this on a calculator. This is just practicing plugging things into a calculator. And I don't think that'll be much credit on the exam, but just practice these, all right? Yeah. On what? I'm using the formula that log base A of x is equal to natural log of x over natural log of A. I think I may have used B here in class. So if I have log base A of B, I do natural log of B over natural log of A on the calculator. Natural log of 12 over natural log of 2. Right into the calculator. Can't plug this in. Well, it depends on the calculator again. Is that a TI? Yeah, I don't think it has that. Yep. Yeah, so 2021 I'm not really a big fan of. Oh, these are good. True or false? Is this true or false? False. You cannot do that. That's like distributing a log through this. What you can do is this. Well, it can't do that. If you have log base A of x times 3, then yes, it becomes this because multiplication becomes addition, right? Okay, is this true? No. This is a log times a log, right? Not a single log with two things multiplied inside. So this is not true. This is false. What about this one? This one's true. Multiplication inside of a single log turns into two logs with addition. How about this one? This power come down? It's false. What is the 2 acting on? The whole log. What does the 2 have to be acting on in order for the property to work? Just on the variable. Very good. Right? So for that to have worked, I would have had to have written it this way. Or in parentheses there, x squared. Then the 2 comes out. But not if there's a parenthesis around the whole log. How about this one? Can I put the 2 and push it up here into the exponent? No, because you have to have logs to pull exponents out and push them up. You got to have logs to begin with, right? There's not. Yes. Is this a true or false? Are these equations true? Like, are you using the property correctly here? Half-life, we've done it. 24, cooling. Metal block is cooling, so its temperature is given by this. Oh, we can do this one pretty quickly. I can talk through it. They give you a temperature function, okay? What is the block's initial temperature? How do you get that? That's the temperature at time 0. Plug 0 into this. What's 4 raised to the 0? 1. 200 times 1? 4 to the 0 is 1. So 200, right? The initial block's temperature is 200. Am I answering? This is the one you asked about, right?
No, I answered
the other one. Okay. How long has it been cooling once the block has a temperature of 100 degrees? So that means all you have to do is take 100 to the left side and solve for T. And that's it. Okay, study, right? There's a lot of material on this test.
Are there any questions you want to cover?
I did say don't do what, 25? Don't worry about 25.
Don't worry about that other.
And then
The population.
the population, 18. And then in the beginning, there was the graphing one, or no, not the graphing one, this one right here. Number 4, part B, I wouldn't worry about. 4B. Yep.
All right, just making sure.
All right.